That's the picture I was looking for. Okay, so what bidirectional search is a kind of alternative method where, so all the methods we looked at so far just expand out from the start node. But if you happen to know where the goal node is, then you can actually search, you can expand from the start node and at the same time expand from the goal node and have two trees that you build up in parallel. And when they meet up, then you found a path. This is called bidirectional search. And this can actually, in the right situation, this can actually be faster than the other searches. Why is that? Well, how many nodes would you generate in the process? Well, let's say the branching factor is B and the length of the shortest solution is D. Because you're expanding these at an equal rate, let's say they met up here, well, this length here would be D over 2, and this length here would be D over 2. So the number of nodes here would be B raised to the power D over 2, and the same thing here. And so the time complexity of this is order 2 times B to the D over 2, which is the same as B to the D over 2. So this is actually a lot smaller than, what's an example? You know, if B was 10 and D was 12, then you're expanding 2 million nodes instead of expanding 1 trillion nodes. So I think I got that right. So that's a huge, if it's a big branching factor, this can be a huge saving. Now, a couple of issues with this. You need to have the right kind of data structure because when you generate a new node here, you have to test to see whether it exists here. And so when we talk about this as being order B to the D over 2, that's assuming that you can do that in constant time using a hash table. Now in practice, instead of a hash table, we might use a binary search tree or something that takes logarithmic time to look something up. So this may turn into a little bit longer than B to the D over 2, but it's still going to be a lot faster than breadth first search. Okay. So there's a hash table. Now, the other issue is you have to know where the goal is, and you have to be able to search backwards from the goal. So in some situations, there may be several goals. If there's multiple possible goals, you don't know which one to be searching from. So you can't really do this. And A-star search can also be used in chess. Is not quite such a good example because it's an adversarial game, but if we think about it, Infinite Mario, you know, there's multiple ending states, and it may not be easy to run the physics backwards to generate it may be impossible, in fact. Or if you're looking at playing pool or something, snooker, it's not easy to go backwards, right? So there's some situations where you just can't really apply this. But when you can, it's quite useful. And this is just a summary of the complexity results for some of these searches. So have a look at this. I mean, it's people have asked, do we need to memorize this table? But it's not really a matter of memorization. It's more to help you think about the algorithms. You know, why is it that the depth first search has complexity order B times M? Oh, it's because of what I just explained, that you only need to keep the path and its successors in memory. You know, why is this B to the power D? Well, there's B branching factor and depth of D, and it grows like that. You know, so try to look at this and ask yourself why each one of these is correct, and it helps you to understand. Okay, any questions about this? Yes.
I have a question. Are there any graphs and searches which kind of have an idea in which direction to go? Like, I'm just thinking if I'm a human and I need to go to the city,
yes.
I approximately know the direction, so I just try to go there first. So are there any graphs and searches that are aware of the physical, like, drawing of the graph and know which direction to go and prioritize it?
I'm so glad you asked that question because that's exactly what we're going to talk about next. Yeah. So the question was, are there searches which have an idea of which direction to go? Yeah. Very good. So the answer is yes. And so let's first look at this in the question of Romania, right? So you want to go to those other searches just expanded out equally. They had no idea whether they were getting closer to Bucharest or farther away. But let's suppose we have a bit of extra information here. For each of these cities, I tell you the distance in a straight line to Bucharest. Right, so this is just the straight line distance. So Arad is 366 kilometers from Bucharest, or miles, or whatever it is. Pitești is 98. So this is an estimate of how far you are from Bucharest. You have to travel along the actual road, so the actual distance you have to travel is going to be greater than this. But this at least gives you some idea whether you're going in the right direction. This is what you were meaning, right? Yeah, very good. So searches that make use of this information are called informed searches, sometimes heuristic search or informed search, and the other ones are called uninformed. Okay, so just to get the overview, so this is the same slide from last time. This is the general structure of all of these search algorithms. So as I mentioned, we have this queue of nodes waiting to be expanded, and the only difference between these algorithms is the order in which they choose those nodes. So breadth first search, new nodes always got added to the back of that queue. So you add new nodes to the back and you pull off from the front, and that gives you the breadth first search. Depth first search, one way to implement depth first search. There's multiple ways to implement depth first search, but one way is just new nodes always go at the front of the queue. So it actually becomes a stack rather than a queue. So these things here, they always do the same thing. Now, uniform cost search, it kept the nodes in order of the path length. So it's a little bit more sophisticated, but we still regard it as uninformed because it's only making use of information as how far you are from the start. It's not making use of how close you are to the goal. So now we're going to look at these informed searches, and there's two main types of informed search. So one of them is called greedy search, and the other one is A-star search. So we'll look at them in turn. Okay, so greedy search. Again, we expand Arad first, but now we're making the choice. So what greedy search does is it always expands the node that's closest to the goal. So if you look at, it's a bit hard to read these numbers, but Sibiu is 200 and, well, you can tell it's closest to Bucharest, right? But this is 253 and Timisoara is 329, right? So it expands Sibiu next. Now I've got a choice of 4 nodes to expand, and it turns out that Făgăraș is the closest, right? Făgăraș is 178 and Râmnicu-Vilcea is 193. So it expands Făgăraș next. So when you expand Făgăraș, then you get here, and then afterwards you expand Bucharest because its distance is 0, right? So this is called greedy search. Now, the reason it's called greedy search is it always tries to get as close as possible to the goal as fast as possible. So it tries to sort of bite off, we think of it as trying to bite off the biggest piece of the problem that it can in one bite. So when it's here, it prefers to jump, in one go it can jump here, so it prefers that over this. Now the thing about greedy search, it often does find, in this case it found a solution extremely quickly, and that is often the case. It's often the case that greedy search finds a solution very quickly, but it doesn't find this optimal solution. In this case, it's only a bit longer than the optimal solution, but sometimes it finds something that's twice as long as the best solution.
So we are expanding on the cities that are closer to the goal.
Closer to the goal.
Why don't we take into account also the distance to the cities, because that's how we ended up with Făgăraș instead of the short way.
Exactly. That's right. Very good. So let's think about that a little bit more. So why it chooses Făgăraș because it's closest to the goal, to Bucharest, but we kind of know that Râmnicu-Vilcea would be a better choice. So try to explain to me why Râmnicu-Vilcea would be a better one to expand.
Well, because it's almost the Bucharest from this wheelchair thingy.
Yes.
The distance to this wheelchair thingy is much less. So if we add up the total
Yes.
expected path to the Bucharest, then the wheelchair becomes better choice.
Exactly right. So Fagaras is, what's the difference here? So Fagaras is 178. Vimnicu-Vils is 193, so that's a difference of only 15, right? But I have to travel 19 extra to get to Fagaras. So I get closer to the goal, but I have to travel further to get there. So I'm traveling 19 kilometers less to get there, and then afterwards the distance is 15 more. So when you add them up, that looks like a better choice. Can everyone see that logic? Yeah, so because you add up the distance actually traveled plus the estimate of this distance. And that should give you a better way to choose the next thing to expand. Very good. And this is called, doing that is called A-star search. Okay, well, just before we get to A-star search, let's just quickly look at the properties of greedy search. It's similar to depth-first search. So in order to be complete, you have to exclude repeated states along a path. Otherwise, if you don't exclude repeated states, let's say you were starting here and you wanted to get to Fagaras, where you could just go back and forth there. So you've definitely got to remove repeated states, but in that case it would be complete. The time and space complexity, well, this is the thing. In general, greedy search is very fast, but it is possible to design perverse graphs in which it actually takes a really long time. Yeah, so the worst case performance is actually just as bad as depth-first search. It's B to the M, and it certainly doesn't find the optimal path. Okay. Good. Okay, so now we get to the main event, really. This is the algorithm we've all been waiting for. This is the algorithm that's, superior to all the others in some sense. So what you do is you take that estimate of the distance to the goal and you add it to the distance already traveled, and you use this function to order the nodes for expansion. And this is a nice way of combining greedy search with uniform cost search. And it's traditional to use these letters F, G, and H for these things. So greedy search only took account of H of n, the estimated distance to the goal. Uniform cost search only took account of G of n, which is the distance already traveled. And A-star search adds the two together. So by adding the two together, we get an estimate of the entire path from the start node through the current node and onto the goal. Okay, so let's look at an example of this. Now, right, I know these numbers are a little bit small, but what I've done here is the numbers in red are the path length, and the numbers in black are obtained by adding the path length to the straight line distance. So between these three cities, Sibiu is the best choice because this number is smallest. So we expand it. And then among all of these choices, the difference is small, but Vimnicu-Vilsia is preferred. This is 413, that's 417. So it expands Vimnicu-Vilsia. And then Pitești. Now, again, at this point we've generated Bucharest, but similar to uniform cost search, we can't finish now because our estimate of the path through Fagara, because we got to the goal, this must be the true length of the path, which is 418. But it's possible there might still be a path through Fagaras that's shorter. Our estimate is 417. It is possible that it's shorter. So we expand Fagaras, and then we find out that this path is actually longer. And in fact, all of these numbers are bigger than 418. So this is the point at which we can stop, and we know that this is actually the shortest path to Bucharest. Okay, any questions about this? The numbers below are the estimate, that's right, the estimate of the path length. But they're always an underestimate. Yeah, they can't be longer than the real one. Okay, so properties of A star search. Yes, it is complete. It's guaranteed to find a solution. The time complexity is a little bit complicated, but there are ways to estimate it. If you can estimate the relative error in the heuristic and multiply it by the length of the solution. But it's still exponential, but usually it's a lot fewer than breadth first search. So again, it's an issue of the worst case versus the normal case. So in most cases, A star search uses a lot less memory than breadth first search, but there are some cases where we still run out of memory and we need to do a slight modification, iterative deepening A star search. And is it optimal? It is guaranteed to find the shortest solution. So I'm just going to show, what I'm going to show you now is a proof. I'm going to prove to you that it's guaranteed to find the shortest solution, and then after that we'll take a bit of a break and then we'll talk about how to find heuristics. Yeah.
H could be anything. I mean, what if it was just easterly direction H? Right, then it wouldn't be good enough for you to get to your...
Right, so the question was H could be anything. Well, no, H has to have the property, it's got to always underestimate the true distance, and I'll explain why. And then in the next hour we'll talk about how to find appropriate. It's got to always be underneath. If it's bigger than the true distance, then you have a problem. It's always got to be underneath the true distance, but you try to get as close as possible without exceeding it. Okay, so why do I say that it's guaranteed to find the shortest path? So let's assume that we've applied the A star search algorithm and it's finished and it's found a path. So what that means is, remember, we don't stop until a goal is actually scheduled to be expanded. So if the algorithm is finished, that means we've found a node G, and this function f is smaller for G than it is for any of these other nodes. Now what does that mean? Well, f is equal to G plus H, but because G is a goal, the distance to the goal from G must be 0, and because H underestimates the distance, H of G must be 0. So this f of G must be actually equal to the true path cost from the start node to G. So in the case of Romania, it was 418 kilometers. Now how do we know this is the shortest? Well, let's consider some other path to a goal, and I have to prove to you that this other path is longer than this one. Now it could be a path to the same, there could be multiple goals. The other path could go to the same goal or it could go to a different goal. Right, doesn't really matter. But whether it goes to the same goal or a different goal, if we start from S and we follow this path, the first few nodes we go through are going to be nodes that have already been expanded, that are in this inner circle. But at some point I'm going to cross this boundary, and there's going to be a node which has been generated but hasn't yet been expanded. So let's call that node N. Now, as I said, it doesn't matter whether it's G or G prime, but for simplicity, let's assume it's a different goal. Let's suppose this path goes down here to G prime. Now, here's this node N. Now, we use H star of N to mean the true path cost from N to G prime. And then H of N is the heuristic. Well, this estimates the distance from N to G prime. So that's the H star is the true value, and this is the estimate. Now, because G was expanded first rather than N, so N had been generated, so it was available to be expanded, but we chose G instead. So it must be that f of G is less than f of N. And f of N is G of N plus H of N. Now, this is where we have to make the assumption that H is an underestimate. We need this assumption in order to prove that the algorithm is optimal. So we assume that H of N always underestimates the true path cost. It's either equal to the true path length or shorter. So if we make that assumption, that means that when we add h of n and g of n, that must be an underestimate of h star of n plus g of n, which is the true path cost. Right, so the whole path cost is being underestimated. So that means that the path length to g is less than the path length to g prime. And that's true for any path to g prime. So this must be the shortest path to a goal. Does that make sense? Yeah. So if you go and have another look at this, have a look at the little video and go back and have a look at this in your own time. But this is the crucial assumption. We need the fact that so you were asking h of n could be anything. No, it has to be an underestimate, yeah. There are some situations in which A star search still runs out of memory. Then we have this alternative which is called iterative deepening A star search. So iterative deepening A star search is similar to iterative deepening search, but instead of limiting the depth of the search, we limit the value of this function f. So we do a depth we choose a certain f, and we do a depth first search only to that depth, and then we increase, and we have to carefully choose how much to increase it by and that sort of thing. So this, you can play with this. I've got the Prolog code for this as well. You can play with that too. Okay, so when we're given a map or a maze, this straight line distance is actually a good heuristic to use. But yeah, when we're given something like the 8 puzzle or Rubik's Cube, this becomes really quite a challenge. Like, if I gave you a particular cube and asked you to estimate from this position roughly how many moves am I away from the goal state, that's not easy, is it? So this is what we're going to be talking about in the second hour. Well, first we'll talk about the 8 mazes and the 8 puzzle, and then at the end we'll talk about Rubik's Cube.